So I'm very pleased to speak at Q2B with Cyril about the work between EDF and Quandela about quantum algorithm for a structural mechanical problem. So Quandela, it's a photonic quantum computing startup. It's a full stack company. It's based in Paris, where we have our R&D center, but we also have like a production center where we make QPUs. We've sold recently a QPU to OVH, a cloud provider, and we also have an accessible cloud compute on the cloud with 6 qubits for now. And maybe to just talk briefly about the technology, so it's photonic. Everything is based on single photons, and we emit in single photons through a quantum dot, so like semiconductor physics. And these quantum dots are state-of-the-art single photon emitter, and like kind of very, very nice for emitting single photons. And so with that, I'll let Cyril talk you through the problem a bit.
Okay, thank you very much. I'm working at EDF. It's a French electric utility company, which is maybe the major actor in the electric market in Europe. EDF was founded in just after the Second World War, but the point is that a research unit it's also was created at the same time, and now it's about 2,000 researchers in this unit based mainly in Paris area. As we have this long history of research and development, we have a culture to develop our own simulation software. As an example, for instance, in 1988, we start to develop finite element software Codaster, which is now open source and used by probably 1,000 engineers to address all kind of subject to simulating dams, nuclear power plants, or some elementary pipes in the circuits. In 2017, so just a few years before quantum revolution came to France, we were already trying to see what could we do actually with quantum computers. In this second wave, we started to look, first it was like combinatorial problem, but then we started to look on the partial differential equation, which is more or less classically solved with finite element software. And we at the beginning were a bit pessimistic, but in a few years, I think we could probably say that even in this decade, we will add a Q to our Codaster to say that it would be quantum finite element software. So I'll try to present you briefly what the problem we were considering. So we took the most relevant, to our opinion, differential equation, which is linear elasticity differential equation. It's Navier-Cauchy differential equation, where you are known, it's a vector displacement field of your structure. It means that you try to figure out if you apply external forces, how your system will deform. And this is elliptic differential equation, so you could rewrite it as minimization of elastic energy, variational problem. If you try to solve it with computer, then you need to discretize your space. And if you discretize your space, then you will end up with some algebraic problem like Ku equal F, where U is vector of unknown, and it could be converted also to minimization problem of some quadratic potential. So in classically, what are the main tasks to do? It's actually to construct this rigidity matrix, which is huge, very sparse, and there's finite element software is used for this. And then you solve the, for sure, the either minimization or straight linear equation. And we were wondering what could we do actually with quantum. So we started for sure like all the beginners. We were advised a little bit by some experts. So there was already in Qiskit some HHL well-known algorithm which should scale up very better than classical algorithm, and we were trying just to say, look, we have a lot of, we are pretty lucky because somebody already solved the problem for us. We were trying to solve it with Qiskit, and that was a little bit disappointing because actually we could reach with like this vanilla solution only 8x8 system size solution, because number of gates to encode the metrics were exploding much faster than we were expecting. And actually, we had even no future point just to, you extrapolate usually, say, look, quantum will reach classical at this level. And classically, you could already solve the system about billions of degrees of freedom. So we are pretty far away and disappointed. That's why we switch our strategy to use something more a short-term solution, more close, is variational quantum linear solver, which were described also by some of the previous speakers. So what the idea mainly is that you first need to map your classical data to the quantum one. That's mapping of unknown is really straight because you take your vector of displacement and you suppose that actually it's a vector of amplitude probability of the quantum state generated by the interacting qubits. So you could see that even with 40 qubits, you already could generate, in principle, representate data compared to classically state-of-art problem. So billions of degrees of freedom. Then what you need to do, it's actually you rewrite your problem, and it's finally it's like a minimization problem of some Hamiltonian right now. And the main issue is still remain. You should encode your matrix. And this, what usually is done, it's you try to decompose in some blocks that you could easily collapse or measure with quantum computer. So we were doing in this strategy. Already some other guys did this close stuff, but we were saying, look, we could try to be inspired by the finite elements themselves. What they do, the finite elements, to construct this huge matrix, it's actually, they represent your structure as blocks of like regular blocks, and each rigidity of elementary rigidity actually the same for all the blocks. So finally, you just calculate it once, and then you plug it to the huge matrix, and so your only the problem is to plug in the right places. So this problem of relating connectivity to the material properties. And we pushed this idea a bit further and said, look, what we could do is actually see that our structure is construction between connection like horizontal one and vertical one. And if you do this, it's actually see that these two contributions, each of them is decomposed in some very straight way. So actually one KAD, it's connectivity itself, it's 2x2 matrix. Then D is diagonal matrix related to the dimension in horizontal dimension. And T, it's toplets like very simple matrix or related to NY direction. And if you try to compute the horizontal part, it's almost the same. You just swap the two matrices. So finally, your problem was decomposed quite straight to the mathematical. So you were before like in mechanics, and now all mechanics was in this K coefficient, and all the computer science actually came to these matrices that we were trying to decompose also in the tensor product. And this was, we were inspired by some works, and the idea that we decompose it in the over-defined basis. So you could decompose it surely for with just a standard basis in the X, Y, Z components, and you could just over-define it in order to reduce number of terms. So we are using some specific projector operator which are not unitary, but the point is that you could still estimate it. Well, oh, it's even not our presentation then. Great.
Could you guide me a little bit and let me know which slide looks right?
Yeah, but I don't care. I will go through. So the idea that this kind of operator is not unitary, but could be realized for some kind of hardware very easily. For instance, if you have a photonic hardware, then you just block one of the propagation level of light. Doing this, then you need to make a supplementary state. I will not go deeper in this. You should encode your quantum representation with some not a classical parameter, and then optimize on this classical parameter your quantum estimation. So it's a hybrid kind of optimization, and we use some of the ansatz we were seeing. And what have been done so far, so I present you first case we were studying. It's not really industrial one, but it's close to industrial. It's a plate where you have a crack inside of it, and you're trying to estimate whether this crack would propagate if you apply the loading, some loading, and how what the opening of this crack is as well, because it's relevant if you have some hydromechanical coupling process where the contaminated fluid would pour out from the crack itself. So the point is that you have two relevant parameters to estimate: crack opening and then profile of your crack, which indicates you whether the crack is going to propagate, which is a material property. So as we were doing first, like Blake-top calculation with simulator, we could also calculate what is current quantum tomography of the state. So finally, on the left, it's quantum realization. On the right, what would be the classical realization in 1988. You see that it's not precisely the same, but what is interesting that you have like some of kind of race, that's if you are using your ansatz and you go, you add up the layers and ansatz, you still converge for these two observable quite nicely to the value, to theoretical value. So finally, we are quite optimistic right now. We haven't done so far simulation on the GPU, and probably I come back to Piere-Emmanuel, who will summarize what are the main stage and what would be the further stage of our calculation.
Thanks a lot, Cyril. So if I want to kind of go through the points that Cyril mentioned, if you want to make sure that you're implementing a VQ algorithm that is efficient, you need to go through this state that we have made through the project. So you need to encode your second member, the vector f, via unitary transformation that is efficiently represented. So we've checked that you can implement this UF with a few Adama gates. So that's fine, that's granted. Then you need to create your variational state, your ansatz, psi. And so there we've kind of benchmarked a lot of ansatz. So we haven't gone through in the presentation this benchmark, but we have checked a lot of them. Because our problem has some symmetries, it's a real problem, then you have some ansatz that, of course, converge faster than other ones because they have less parameters. So this is something we have checked. I guess the main point from the presentation is that we have this decomposition of the rigidity matrix in terms of a simple tensorial product of polynomially many terms. And it's very important because this is how we evaluate our loss function. So we need our loss function. So this is basically the energy. We want to minimize the energy, and this loss function, it needs to be obtained in efficiently, right? So you need to have at most polynomially many terms. So we've checked that this is the case, and we've managed to find an encoding for it. And lastly, once you have your optimization succeeded when you converge, so it's not guaranteed you're going to converge, so that's the main point of quantum machine learning. But if you do converge, the nice property of that problem is that you can take the insight of, your physical insight of the problem, and you realize that the only information you need at the end is to make a few measurements around the crack only, because you want to know how the crack is going to evolve in your structure. And so that's very important, because if at the end of the algorithm you have your information that is encoded into the entire state, then you would need to do full tomography, so that wouldn't be interesting, because you would need an exponential number of measurements. But here you can retrieve the interesting aspects of your algorithm into a few quantum measurements at the end when the algorithms have converged. So that's very nice. And then to sum up, so we've tackled a structural mechanics problem which is a use case that EDF is very concerned with. So like basically cracks, evolvement of cracks in dam or nuclear pipes. We've managed to do an energetic formulation in a VQA setting, because we realized that the standard HHL or VQLS algorithm were not very suitable for this type of problem, so our rigidity matrix didn't have the right properties to be encoded efficiently in that type of algorithms. And then we show that we have a variational algorithm that is efficient. So efficient in the encoding of the classical data, efficient in the decomposition of the rigidity matrix, with a few numbers of, so not Pauli terms, but these projectors that Cyril was mentioning. And then you can take a few measurements around the crack to get the values of interest. And so I guess the outlook, it would be very nice if you could prove rigorously that you could converge at any number of nodes. Of course, it's very difficult. Like, for instance, in classical machine learning, it's very hard to prove convergence. So here is the same, but you can at least prove that you have an expressive enough ansatz to reach the value. And then we're currently working on getting this. So what you saw in the presentation was a simulation, and now we're working on having it working on our hardware, on our QPU. And you can stay tuned. The archive paper is coming out shortly, I guess beginning of 2024. And with that, I'd like to thank you for your attention.
Thank you. So unfortunately, the next speaker had to cancel, so we have some time for questions. I'll bring the microphone to you.
Thanks for that very nice presentation. This is Madhav Shamlal from Qubit Solve. A couple of quick questions. So in your ansatz, did you restrict to just real amplitudes, or did you also use the complex values? That's one. The second question is, what optimization algorithm did you use to find the parameters? Thank you.
Good answer. So actually a good question, because right, our variable are real. So actually we were wondering what better to use, and we checked multiple solutions. So first we used, if you've seen real ansatz, actually. So you stay in real world, but then actually you could use also complex one and stay, you know what the convergent state is real, actually, and you converge still to a real value.
Yeah, I think the other part of the question was about which
convergence
optimization method you use.
Yes, that's a good question as well.
I can take this one. So I guess we've tested a lot of optimizer, and then it depends what type of backend you're using. So if you have if you're dealing with like sampling, like finite sampling issues, then you're better off with noisy optimizers. And if you do exact simulations, then you can use, I don't know, BFGS, for instance, or any gradient descent methods. What we haven't implemented yet, and I think it's worth checking, but it's work in progress, is a shift rule, I guess, also. So in some cases, it's possible to actually compute the gradient from your quantum circuit. And it's something we would like to also perform to get a native quantum computation from the optimization as well. Does that answer your question? Good.
Thank you for your thorough presentation. I just want to ask about the Baron-Plateau issue in your optimization. Is your model robust enough to just get optimized, and how many Baron-Plateaus or challenges do you have, and how much is dependent on the initial state of your parameters? And yeah, that's.
Okay, I could first.
Yeah, I complete if you. Yeah.
So first of all, something which is quite different from machine learning here is that we have really minimization problem. So actually, our cost function has a minimum, and it's proven. So finally, you could use even not the optimization based on the gradient or on the second derivative, but on the alternative minimization, because you know that you will go through to some minimum. So you could solve this issue this way. But then we've seen in practice that they are present. Somehow the troubles are there because we were not converging all the time to the same values.
Yeah. But if I want to complete, so if you do exact simulations, state vector simulation,
Quite robust.
Yeah, it's quite robust. So I guess the problem with Baron-Plateaus is you don't really know when it's going to happen, and for what we checked, it's fine. Like we converge all the time. But maybe when you go to larger and larger dimensions, they will appear at some point. But for now, what we checked, still not. And so I guess also the next step will be to take GPU simulations to get to like very large number of qubits. And I guess we hope that, Baron-Plateau won't show up there.
And then you could also, as you said, use the initial guess of the solution to be more close to the solution. It's quite easy to actually set up this type of, because we actually used the probabilistic random vector, initial vector, and that was some influence, but not so big. But I suppose when we would do the high dimensional system, it would appear, so you could check whether the initial state has influence as well.
Yeah, and I guess if Baron-Plateaus do show up, what's nice is that we have experts in like structural mechanical problems, and so I guess, so we've discussed it before. I guess it's okay to come up with good heuristics for the initial state. So that would be, I guess, a solution if they do show up, but they don't show up for now, so that's fine.